Hi everyone, in this video we're going to talk about some of the tools that you're going to need to verify trig identities. So we need to start off with what is an identity, and then from there get a list of our fundamental trig identities that we are allowed to just assume are true and then use to verify other potential trig identities. So I think the easy spot for confusion here is the difference between an equation and an identity. So if we think about, I don't know, let's just say I said sine x is equal to cosine of x. So this is a statement, and this statement is going to be true depending on the value of x that you choose. So this is not true all the time. Sine x and cosine x are different functions, but if you think about their graphs cross, and wherever their graphs cross, sine is equal to cosine. So in general, the idea with equation is find the values of x that make the statement true. But sometimes something really interesting happens, and it turns out that it doesn't really matter what x you choose. The statement is true in general, and that's when we have an identity. At that point, we're not looking to solve. We just have like a fact in front of us, something that is true regardless of the value of x that you choose. So we want to take statements involving trig functions and decide whether or not they are identities, decide whether or not they're true for all x. And the way we'll do that is by using our fundamental identities and by trying to turn the statement that we've got back into something that's clearly an identity. So one of these, or something like 1 equals 1 is definitely an identity. So that's going to be our goal. Okay, so the fundamental trig identities, these are our building blocks and our tools that we use for verifying other identities. We have two quotient identities, and I'm using this triple equal sign here just to show equivalent. So this is kind of saying that this is saying it's an identity, basically, that these two functions are equivalent. So quotient identities tell us that tangent x is equal to sine x over cosine x, and that cotangent x is equal to cosine x over sine x. We also have, technically there's 6 reciprocal identities. I've listed 3 because I think it gets a little silly to list all of them, but I'll make sure that I mention them. So first one I wrote down is that cosecant is equivalent to, cosecant x is equivalent to 1 over sine x. And the other one that goes with this would be sine x is equivalent to 1 over cosecant of x. So this is what I'm saying, where there's actually 6, even though I wrote down 3. But I think just saying secant is the reciprocal of cosine covers both of those. And cotangent is the reciprocal of tangent. This one can get into a little bit of funny trouble when you're at the odd multiples of pi over 2. So for example, if I'm at pi over 2, at pi over 2, my coordinates are 0, 1, which means cotangent by definition should equal 0 divided by 1, which is 0. Tangent is 1 divided by 0, which is undefined, and 1 over undefined is not 0. So we have a little bit of a problem right at the asymptotes of whichever function is on the bottom. Otherwise, this will work. So as long as we leave out the certain quadrant angles that give us trouble, this will be true. There's actually 3, even though I've written down only 1. The last 3 are the Pythagorean identities. So this first one is just our usual x squared plus y squared equals 1. I guess I have it in the other order, y squared plus x squared equals 1. So this is true, again, no matter what arc length you choose. Wherever you are in the unit circle, this is always true. And we can use this one to generate the other 2. So hopefully you've got everything I have written down right now memorized. These 2 you might have to memorize, but I would just say that the way I cope with this is I don't remember them generally. I have kind of the right idea. I know one of them is going to involve tangent and secant, and one of them is going to involve cotangent and cosecant. But to remind myself exactly how they're set up, they're similar but not quite the same. I just go through this, and to get one of them, you would divide both sides of this identity by sine squared, and in the other one, you divide both sides by cosine squared. So if I divide both sides by sine squared, I would get sine squared x over sine squared x, which is 1. And then I would get a cosine squared x over sine squared x. And just to make sure everyone's clear on that, what that really means is I have cosine x squared on the top, and I have sine x squared on the bottom. And that should be still equivalent to 1 over, oh wait, sorry, I'm getting ahead of myself. So this is what I was working on, cosine squared over sine squared. This is exactly the same as having a cosine x over sine x all squared, which is a cotangent of x squared. So this turns into cotangent squared x. And then 1 over sine squared, similarly, you can move that squared out and put parentheses around the whole fraction. And what you're really getting there is a cosecant squared x. So there's one of them. Notice sine squared plus cosine squared equals 1. The 1's by itself here. These, unless you rearrange, you're going to have 1 plus one of these trig functions. And even if you do rearrange, that will turn it into a minus. So they're a little bit different. To get, so this is number 7. To get number 8, you would divide both sides by cosine squared. So you'd get sine squared over cosine squared, which becomes a tangent squared. You get cosine squared over a cosine squared, which is a 1. And you get 1 over a cosine squared, which is a secant squared. So these are our 3 Pythagorean identities. And this is kind of the beginnings of the thought process for verifying identities. Kind of backwards, I guess. With the verifying, we would start with one that we weren't sure about and see if we could work our way backwards using things that we do know. But still kind of a similar process. We've got an identity. Can we manipulate it to get another identity? Okay, so this is what we'll need to know. If any of these are not already stuck in your memory, make sure you get them stuck in your memory. And then I will just work through a bunch of examples for you to try and help you get going. Thanks for watching.